Okay, in this lecture we're going to start our Chapter 13 material on integral calculus. So far what we've been studying in the course is differential calculus, which is the process of finding the derivative of a function, which represents its instantaneous rate of change, or geometrically the slope of the tangent line to the graph of a function at a given point. So in Chapter 13, where we're talking about integral calculus, we're working in the opposite direction. The main idea here will be if we know the derivative of a function, how can we work backwards and find the original function, which has that given function as its derivative. So these types of problems involve finding something called an antiderivative. So in section 13.1, we're going to talk about antiderivatives. And let's start with a definition. What is an antiderivative? So we would say that a function capital F is called an antiderivative of a function little f on an interval if the derivative of capital F of x is equal to little f of x for all values of x in that interval. So throughout this chapter, when we're talking about finding an antiderivative of a given function, little f, we're looking for the function capital F whose derivative is equal to the given function. So that is, if we're given the derivative of a function, we want the original function capital F. So this process is called anti-differentiation or integration, which we'll discuss a little bit later in this section. So as sort of an introductory example, let's consider the following problem. Something nice throughout this chapter is if you think you found an antiderivative of a function, can you check your answer? So this is that sort of problem. Can we show that the function capital F of x, which is defined as x times log x minus x, is an antiderivative of the function natural log of x? So to show that this is an antiderivative, we would look at the derivative of capital F of x, and here we have to make use of the product rule since we're looking at x times natural log of x. So for the product rule, we first take the derivative of the first function in our product, which was x, so its derivative is 1. Then we multiply by the second function in our product, left alone, so just natural log of x. And then we add the product of our first function, left alone, so just x, and the derivative of natural log of x, which is 1 over x. And then our last term on the end, we were subtracting an x, so here we subtract the derivative of x, which is 1. So simplifying, we have the natural log of x plus my x times 1 over x is simply 1, and then I'm subtracting 1. So my plus minus 1 cancel, and I'm left with just the natural log of x, which was my little f of x function. So since the derivative of capital F of x is equal to the given function, little f of x, we can say that capital F of x, which was x times log x minus x, is an antiderivative of the function little f of x, which was the natural log of x. So throughout this chapter, it's often helpful to check our answers. If we think we have found an antiderivative of a function, how can we check to make sure that we did indeed find an antiderivative? Well, if we differentiate the function, we should get back the given function. So let's look at another one. In our next example, we're asked to show that the function capital F of x, which is x squared, is an antiderivative of 2x. And then we're asked the question, are there any other antiderivatives? So for this one, it's pretty straightforward. The first part, we can say since the derivative of capital F of x, which was x squared, is equal to 2x, which was our little f of x function, capital F of x, which is x squared, is an antiderivative of the function little f of x, which was 2x. So that was the first part of this problem. The second part asks, are there any other antiderivatives? So something to remember from our differentiation material is that the derivative of any constant is equal to 0. So let's suppose that we consider another function, let's say capital G of x, which is going to be the same as capital F of x, that is x squared, which we've already shown is an antiderivative, but I add 1 to it. So if I differentiate this function, capital G prime of x, well, the derivative of x squared is 2x, and then plus the derivative of my constant 1 is 0. So my derivative would still be 2x, which is the same as f of x, which means that capital G of x, x squared plus 1, is also an antiderivative of 2x. So we can say, so capital G of x is an antiderivative of my function little f of x, which was 2x. So there is another antiderivative, and more generally, we could consider a function of the form g of x is equal to not just x squared plus 1, because the derivative of any constant is 0. It doesn't matter what constant I add to my x squared term. So more generally, if we were to consider x squared plus c, where c is some constant, the derivative of this function would still just be 2x. So what we find is that there are infinitely many antiderivatives of this function, which would have the form x squared plus some arbitrary constant. It doesn't matter what constant I add. So we can summarize this result that we're seeing in this last example in the following theorem, which says if capital F and capital G are both antiderivatives of the same function, say little f, then there is some constant capital C such that f of x minus g of x, the difference between these, as we saw in this previous example, f of x was x squared, g of x could be x squared plus some constant. So the difference of those functions would just be some constant. So this theorem says that any two antiderivatives of a function differ by some constant. And moreover, if f is an antiderivative of some function little f, then every antiderivative of our function has the form capital F of x plus c, where c is a constant. So in other words, if we find one antiderivative of a function, we found all of them because every antiderivative of that function would be the antiderivative that we found plus some arbitrary constant that we usually denote by capital C. So this process of finding antiderivatives, or a family of antiderivatives of a function, is known as integration. So let's introduce a little more terminology and notation before we move forward. So we would say that the family of all antiderivatives of a function little f is given by something called the indefinite integral. So here, the notation that we're going to use is the following. So we have this elongated S-looking symbol, which is called the integral sign. Then f of x, which appears after that, is called the integrand. It is the function that we're trying to find the antiderivative of. And then this dx term on the end, the differential of x, indicates that x is the variable of the function whose antiderivative is to be found. So here, if we're working with the function f in terms of x, we would have a dx on the end. If we had a function of, say, t, we would have a dt on the end, and similar. So the indefinite integral of a function is the family of all antiderivatives. And we said, well, if we find any antiderivative, let's say capital F of x is just some antiderivative of our function little f, then every antiderivative would be given by that function plus some arbitrary constant c. So when we're talking about finding an indefinite integral of a function, we're talking about finding all antiderivatives of that function. And this process is known as integration. So let's look at some rules for integration. Those are evaluating, evaluating antiderivatives of a function. So we'll sort of have the same build-up that we did for our rules for differentiation, but now for antiderivatives. So the first rule that we'll start with is the antiderivative of a constant. So if f of x is equal to some constant function, say a constant k, then the integral of k with respect to the variable x would be that constant k times the variable x plus some arbitrary constant. And we can sort of check our work here. If this antiderivative we call capital F of x, let's see why this would be an antiderivative. So if we take the derivative of this function, well, the derivative of k times x is equal to k, plus the derivative of any constant is 0. So we see that the derivative would just be that constant k. So let's look at some examples of just finding the indefinite integral of some constant functions. So in part A, we're asked for the integral of 5 dx. So using our new rule for the antiderivative of a constant, we would have the constant 5 times whatever variable we're working with. In this case, since we had a dx, that means the variable of interest is x, and then we can add any arbitrary constant c that we want, and this would still be an antiderivative. So in part B, we have the antiderivative of 5 dx, pi dx. Now pi is just a constant, so we would have that constant pi times the variable that we're working with. In this case, we had dx, so our variable is x, plus any arbitrary constant c. And in part C, we have the square root of 2, which is just some constant here, dt. So we're going to take the same constant, square root of 2, and then multiply by whatever variable we're working with. In this case, the variable t, since we had that dt on the end. And then we can add any arbitrary constant that we want, and we still have an antiderivative. And again, keep in mind throughout this chapter, one way to always check your answer is if you differentiate this answer, you should get back the function that you were taking the integral of. So for each of these parts, if we were to differentiate the answer that we found, we would get back the constant that we started with. So one way to check our answers throughout this chapter 13 material. So let's look at some other ones, maybe a little more complicated. So the next simplest type of function, other than a constant function, would be a power function. So our next rule for finding an antiderivatives is called the power rule. And it says for any real number n other than -1, if we're looking at the antiderivative of x to the nth power dx, that antiderivative should be given by x to the n plus 1 divided by n plus 1, and then adding some arbitrary constant c. And this sort of makes sense if we think about the process for finding the derivative of x to the n power. Well, we would take the power of n, there's a little scratch work up here, if we're differentiating x to the n, we pull the power n out in front, and then we decrease the power by 1. So if we want to find the antiderivative for x to the nth power, well, we need to sort of undo this process of differentiation. So instead of subtracting 1 from the power, I'm adding 1 to the power of x. And then instead of multiplying by the power out in front, we're dividing by the power n plus 1. So again, let's see why this works. If we're calling this function capital F of x, then differentiating this function, well, we have a constant 1 over n plus 1 out in front, and then the derivative of x to the n plus 1 would be n plus 1 times x to the n plus 1 minus 1, which just gives us x to the n. So these terms cancel, and we're just left with x to the n power. And then our constant on the end, well, the derivative of any constant is 0. So we can see that we do indeed get back x to the nth power for our derivative. Now, the one condition to watch out for here with the power rule is that this result does not hold if n is equal to -1. So let's think about why not. So if we had x to the -1 dx, well, that's the same as 1 over x dx. So if we tried to apply this rule, we would take x to the n plus 1. So if we have the -1 plus 1, we would have x to the 0 power. But then we would be dividing by 0, which is undefined. So this rule does not hold for the function 1 over x, or x to the negative first, but it works for every other power of x. So let's look at some examples making use of this power rule. In our next example, part A, we have the antiderivative, or the integral, of x to the 6th dx. So using the power rule, we would increase the power of x by 1, so we get x to the 7th, and then we're dividing by 7. And then adding any arbitrary constant c on the end. Or sometimes people will prefer to write this as 1/7 times x to the 7th plus c. It's really just a matter of personal preference. Either notation is perfectly fine. Now in part B, we have the function 1 over t cubed dt. So it may not look like a power rule function or example at first. But if we recall that 1 over t cubed is the same as t to the -3, now we see that we could use the power rule to to find our antiderivative. So to use the power rule, we're supposed to take the function and add 1 to the power. So here we would have t to the negative 2, and then we're dividing by that same power, negative 2, and adding some arbitrary constant, c, to this. Or if we prefer to use positive exponents, well, t to the negative 2 is the same as 1 over t squared. So we have a negative 1 over 2t squared plus some constant if we prefer. But again, either notation would be fine here. Now in part C, we have the indefinite integral of the square root of x dx. So recall that we can rewrite the square root of x as x to the 1/2 power. So using the power rule to find our antiderivative, we take x and we add 1 to the power, so that gives us the 3/2 power, and then we're dividing by that same value, 3/2. Then we add some arbitrary constant c. Now to simplify this a little bit, recall that to divide by a fraction, say divide by 3/2, that is equivalent to multiplying by the reciprocal of the denominator. In other words, multiplying by 2/3. And then we had our x to the 3/2 plus c. So the antiderivative of square root of x, or x to the 1/2, is 2/3 x to the 3/2. That 2/3 out in front is coming from the fact that we were dividing by 3/2, which is equivalent to multiplying by the reciprocal of 3/2. That is 2/3. And then in part D, we have the integral of 1 over the cubed root of x to the 4th dx. So we can rewrite this as the integral of 1 over x to the 4th, and the cubed root is the same as the 1/3 power. Or this is the same as 1 over x to the 4th raised to the 1/3 is the same as x to the 4/3 power, using properties of exponents. But then, just like our part B example, if we have 1 over x to the 4/3, well, that's the same as x to the negative 4/3 dx. So, using the power rule, if we add 1 to the power of x, we would have x to the negative 1/3, and then we're dividing by negative 1/3, and we can add any arbitrary constant c. So simplifying a little bit, my division by a negative 1/3 is the same as multiplying by the reciprocal of negative 1/3. That is negative 3. And then our x to the negative 1/3 power, let me maybe just write it like this for now, then that x to the negative 1/3 power is the same as dividing by x to the positive 1/3, which is the cubed root of x. So rewriting this a little bit, we have a negative 3 over the cubed root of x plus an arbitrary constant. So let's look at some other examples. So the next rules that we'll look at summarize some other properties of antiderivatives. So here, if f and g are functions which have antiderivatives, and k is some constant, so some real number, then the first property we'll talk about is a result known as the constant multiple rule. So just like we had for derivatives, where the derivative of a constant times a function is equal to the constant times the derivative of a function, if we're trying to find the antiderivative of a constant k times a function, little f, that's the same as the constant k times the antiderivative of f of x. In other words, you can pull these constants out in front of your integral. And the second part of this theorem is a result known as the sum difference rule, just like we had for derivatives. If we're taking the antiderivative of a sum or difference of two functions, say f of x plus g of x or f of x minus g of x, that is equal to the sum or difference of the antiderivatives of those individual functions. In other words, you can find an antiderivative of a sum or difference of a bunch of terms by taking the antiderivative of each piece individually. So let's look at some examples of this. In part A, we are asked to find the integral or antiderivative of 25r squared dr. So here r is the variable of interest. So to start using the constant multiple rule, I can pull the constant 25 out in front. I'm left with the antiderivative of r squared dr. And then using the power rule, the antiderivative of r squared would be r cubed divided by 3 plus some arbitrary constant on the end. So let's see what we have. Simplifying a little bit, we have a 25 r cubed divided by 3, or 25 over 3 r cubed, plus some arbitrary constant c. So this would be our antiderivative. Now in part B, we have 10 over t squared dt. So again, using the constant multiple rule, I can pull the constant 10 out in front, and then I have the integral of t, 1 over t squared, which is the same as t to the negative 2 dt. And then using the power rule, well, the antiderivative of t to the negative 2 would be t to the negative 1 divided by negative 1. And then we can add any constant c that we want on the end. So simplifying a little bit, for our first term, we have a 10 divided by negative 1, which is just negative 10. And then our t to the negative first power is the same as dividing by t to the first power. And then we're adding some constant c on the end. Now in part C, we have the integral of a polynomial function, 2x squared plus 3. So that is just a sum or difference of a bunch of power function terms. So making use of the sum difference rule and the constant multiple rule, this is the same as finding the integral of 2x squared dx plus the integral of 3 dx. So for our first term, we can pull the constant 2 out in front, and we have the antiderivative of x squared dx plus the antiderivative of 3 dx. So our first term, we have a 2 times, using the power rule, the antiderivative of x squared would be x cubed divided by 3, plus using the constant rule, or the antiderivative of a constant, the antiderivative of 3 dx would be the constant 3 times x. And then, of course, we can add any constant c that we want on the end. Or simplifying this a little bit, this is 2/3 x cubed plus 3x plus c. All right. So in this example, part C, we showed in full detail that we could take the antiderivative of this sum and split it into the sum of the antiderivatives, pull out the constant 2, and then use the power rule and constant multiple rule and so on. But to save ourselves a little time, as we get more familiar with finding antiderivatives and move through this chapter, notice that my original function, 2x squared plus 3, rather than writing out each intermediate step to find my antiderivative, I could think of this just like we did for differentiation. I would first find the antiderivative of 2x squared. So I would have a 2, and then I increase the power of x by 1, giving me x cubed, and then divide by 3. So I could move directly to the 2/3 x cubed there. And then plus, moving to my next term, I had a constant 3. So I would add the antiderivative of that, which would be 3 times x, and then include my constant c on the end. So as we keep moving forward, I will no longer write out all of these intermediate steps where I split the sum and pull out constants and so on. We can perform those steps and get our answer directly from the function. So let's look at some other examples. In part D, we have the integral of this polynomial function of y. So using our sum difference, power rules, constant multiple rules, and so on that we've talked about, we know that we can find the derivative, the antiderivative of this function piece by piece. So starting with 5y cubed, well, for our antiderivative, we would have 5 times y to the 4th divided by 4, or simply 5/4 y to the 4th. Then we add our next term. We take the antiderivative of 5y squared, which would be 5 times antiderivative of y squared is y cubed divided by 3, or a 5/3 y cubed. Then for our next term, we're subtracting the antiderivative of 10y to the 1st power. Well, we have a 10, and then the antiderivative of y to the 1st would be y squared over 2, or this negative 10 over 2 will simplify to negative 5. And then minus, on the end, we had a constant 6. The antiderivative of a constant is just that constant times the variable that we're working with, in this case, y. And then, of course, plus any arbitrary constant c that we want will still give us an antiderivative. So simplifying just a little bit, we have 5/4 y to the 4th plus 5/3 y cubed minus 5y squared minus 6y plus c. All right. Now in part E, we're looking at the antiderivative of a rational function, or, well, not technically a rational, but a quotient of two power functions. So we had seen from our chapter 12 material that the derivative of a quotient was not just equal to the quotient of the derivatives of the top and bottom. We had a little more complex approach using the quotient rule. So it stands to reason that the antiderivative of a quotient is not simply the quotient of the antiderivatives. So how can we handle this? Well, in this example, we can think about splitting our fraction into two parts. So we could think about taking x cubed divided by the square root of x, or x to the 1/2, and then plus 1 over the square root of x, or x to the 1/2. So if we split our fraction into the sum of two separate fractions, we have the following, which we can then simplify as follows. We have the integral of, well, our first term, x cubed divided by x to the 1/2. That's the same as x to the 3 minus 1/2. So recall, when you're dividing power functions, you would subtract the exponent of the denominator from that of the numerator. So my 3 minus 1/2 gives me 2.5, or 5/2. And then plus the 1 over x to the 1/2 is the same as x to the negative 1/2 power. So now my function is just the sum of two power function terms, just x raised to some power. So using the sum rule, I can find the antiderivative of each piece. So for x to the 5/2, I'm going to add 1 to the power. So that gives me x to the 7/2. And then we're dividing by 7/2. Then we add the antiderivative of x to the negative 1/2. Well, we add 1 to the power. So we have x to the 1/2. And then we're dividing by 1/2 and adding an arbitrary constant c. Or to clean up our answer a little bit, rather than thinking about dividing by these fractions, remember that dividing by a fraction is equivalent to multiplying by its reciprocal. So our first term, where we're dividing by 7/2, that's equivalent to multiplying by 2/7, our x to the 7/2 power. And then plus the second term, where we're dividing by 1/2. Well, that's the same as multiplying by 2. And then our x to the 1/2 power, or square root of x. And then plus a constant c. So we've got the following. Now in part f, we have the integral or antiderivative of x squared minus 1 quantity squared. So that is a composite function, and thus far we don't have a general way to find an antiderivative of composite functions. We'll talk about that a little bit more in our next section. But we could think about writing this as the integral of x squared minus 1 times itself. So here we have the antiderivative, or the integral of a product, but we saw from our chapter 12 material, chapter 12 material, that the derivative of a product is not simply the product of the derivatives. So the antiderivative of a product will not be just the product of the antiderivatives. So how can we handle this? Well, if we expand the x squared minus 1 times itself, we would have x to the 4th power minus 2 times x squared plus 1 dx. And so we now just have the integral of a polynomial. So using the same approach that we used in our earlier examples, the antiderivative of x to the 4th would be 1/5 x to the 5th, or x to the 5th divided by 5, minus, we had a constant 2, and then the antiderivative of x squared would be x cubed divided by 3, or negative 2/3 x cubed, plus the antiderivative of 1 dx is 1 times x, and then we can add any constant that we want on the end. All right. So let's look at some other rules for finding antiderivatives. So of course, not every function is a polynomial. So what if we're working with exponential functions? How can we find the antiderivatives of exponential functions? So here, let's start by looking at the antiderivative of e to the x. Now we know that the derivative of e to the x is itself, it's e to the x. So the antiderivative of e to the x is also e to the x. And then we've said we could add any arbitrary constant c on the end. And of course we can check that if we were to call this function capital F of x. If we take the derivative of e to the x plus some constant, we have e to the x plus 0, which is the function that we were trying to find the antiderivative of. So this works. Or more generally, what we'll see is something of the form e to the k times x, where k is some real number other than 0. So maybe like e to the 2x or something. And in this case, the antiderivative would be e raised to the same function, kx, and then we multiply out in front by 1 over the constant k, and we can add any arbitrary constant c we want on the end. And of course, we can check this if we call this function capital G of x, then taking our derivative, well, we have a constant 1 over k out in front, and then the derivative of e to the kx, using the chain rule, would be e to the kx, but then we multiply by the derivative of that inner function. So the derivative of kx is equal to k, and so our k with the 1 over k cancel, and we're left with just e to the kx. So this formula does indeed work. So let's look at some examples of finding antiderivatives or integrals of functions involving exponentials. So in part A, we have the integral of -7 e to the x. So of course we could pull out our -7. We have the integral of e to the x dx. So that is -7, and then the antiderivative of e to the x is e to the x, and we can add any arbitrary constant c we want on the end. Now in part B, we have e to the 5x dx. So using the second part of the theorem we just looked at, we would have e to the same power, 5x, and then we have to multiply out in front by 1 over that constant, in this case 5. And then we can add any arbitrary constant c we want on the end. Now in part C, we have the integral of e to the 4x minus 4 e to the x. So using our new rule for finding an antiderivative of an exponential function, the antiderivative of e to the 4x is 1/4 e to the 4x, and then we're subtracting the antiderivative of 4 e to the x, so we pull out our constant 4, and then the antiderivative of e to the x is just e to the x. And we can add any arbitrary constant c that we want on the end. Then in part D, we have 12, or the integral of 12e to the -3x dx. So here we can pull out the constant 12, and then we're multiplying by the antiderivative of e to the -3x, which would be e to the -3x times 1 over -3, or a -1/3. Plus any arbitrary constant c that we want. And simplifying a little bit, where I've got my 12 times a -1/3, that gives me a -4 e to the -3x plus c. All right. So we've talked about antiderivatives or integrals of exponential functions. So now what about something that involves a logarithm? So recall earlier when we were looking at the power rule, we said the antiderivative of x to the n dx is x to the n plus 1 over n plus 1 plus c, as long as n was not equal to -1. So in this next theorem, let's talk about the antiderivative of x to the -1. So for any interval which does not contain the value x equals 0, the antiderivative of x to the -1 dx, which is the same as 1 over x dx, is given by the natural log of the absolute value of x plus any constant, because remember, the derivative of the natural log of absolute value x is equal to 1 over x. And this works as long as we're not looking at any interval which contains x equals 0, because of course 1 over 0 would be undefined. So here we recall that the antiderivative of 1 over x is the natural log of the absolute value of x. So let's look at some examples. So here again we're asked to find the indefinite integral for each function. And in part A, we have 9 over x. So that's simply the 9 times the antiderivative of 1 over x dx, which we just said is the natural log of absolute value x. And then we can add any constant we want on the end. So we have 9 natural log of absolute value x plus c. In part B, we have the antiderivative of 8e to the 4x minus 3x to the negative 1. So for our first term, we have an 8, and then the antiderivative of e to the 4x is 1/4 e to the 4x, minus we have a 3 times the antiderivative of x to the negative 1, we just said is the natural log of absolute value x, and then we can add any constant c that we want on the end. So for this first term where I have my 8 times 1/4, that reduces to 2 e to the 4x minus 3 times the natural log of absolute value x plus c. And in part C, we have, again, an antiderivative or an integral of a rational function, a quotient of 2 polynomials. And as we mentioned, well, the integral of a quotient is not just the quotient of the integrals. So, like we had seen in our earlier example, let's try splitting this fraction into smaller pieces. So I can think about this as 2x cubed divided by x minus 3x divided by x, and then plus 6 divided by x dx, which simplifies as follows. My 2x cubed over x is 2x squared, minus the 3x divided by x is 3, and then my last term is still 6 over x dx. So finding the antiderivative piece by piece, well, for the antiderivative of 2x squared, we would have 2x cubed divided by 3, or 2/3 x cubed, minus the antiderivative of 3 dx would be 3 times x, and then plus we have a 6 over x, which is the same as 6 times 1 over x, so we would have 6 natural log of absolute value x plus some constant c. All right. So in the last part of this section, we'll talk about some applications of antiderivatives or integrals. So the primary application comes comes in the event that you're given the derivative or the rate of change of some function, and you're trying to find the function itself. So we'll look at several examples like that throughout this chapter, starting with some simple ones in this section. So in our first example, we're given that the rate of change of the size of the crowd, measured in people per hour, at a certain theme park is given by the function p prime of t is 2800 minus 400t, where t equals 0 corresponds to the opening of the park at 8 a.m. So given that rate of change for the crowd size, we're supposed to, in part A, find the function p of t, which has that derivative, and would give the size of the crowd t hours after opening. So to find the original function, which has this as its derivative, we're going to take the antiderivative of that function. So that is p of t will be the antiderivative of the derivative, which was 2800 minus 400t dt, since t is our variable here. So, like we had seen in our earlier examples, we can find the antiderivative piece by piece. So for the first term, 2800, which is a constant, we have that constant, 2800 times our variable, t. And then minus the antiderivative of 400t to the first power would be 400 times t squared over 2, or that 400 divided by 2 gives us 200 t squared, and then plus some constant on the end. Now, in these sort of problems, when we were just finding the antiderivative earlier, c could be any arbitrary constant that we want. But when we're talking about a problem that has some sort of physical interpretation, like say the crowd size or number of people in a park at some given time, we know that c shouldn't just be any arbitrary constant. It has to be some specific constant that makes sense in relation to the problem. So let's think about what additional information we could use that would allow us to solve for a specific constant c so that this makes sense. Now, we're told in the problem statement that t equals 0 corresponds to the opening of the park at 8 a.m. So if the park first opens at 8 a.m., that means that the crowd size at that initial moment that it opens would be 0. There's nobody in the park at the exact moment that they open their doors. So using that fact, we can say that the crowd size, p, at time t equals 0 is equal to 0. Now let's think about what that gives us for our problem here. So taking our p of t function and substituting 0 for t, well, we would have 0 minus 0 and then plus this constant c. So p of 0 is equal to the constant c, which should be 0 because there is no crowd in the park at the moment that they first open their doors. And so taking the value for our constant c to be 0, we're simply left with p of t is 2800 t minus 200t squared. All right. So in this part A example, we saw that we found our antiderivative. It depended on some arbitrary constant c, but by using a little additional information about the problem statement, we could solve for a constant c so that this function makes sense in relation to the problem. So this sort of condition that we used, where the crowd size at time 0 was equal to 0, this sort of condition is what's called an initial condition. We'll talk more about that in more detail later in this chapter 13 material. So now that we have this function for crowd size, in part B, we're asked when is the crowd size at a maximum. So there's a couple of ways that we could go about doing that. If we think back to our chapter 12 material, well, to find the local or absolute extrema of some function, we would look for its critical values by taking the derivative of our function p prime of t, which was actually given in the problem statement as 1200 minus 400t to the first power, and we would set that equal to 0. So we have 2800 has to equal 400t. So dividing both sides by 400 we find that t has to be 7. So in the problem statement, we were told t equals 0 corresponds to the opening of the park at 8 a.m., and then our rate of change was being measured in people per hour. So t is measured in hours here. So 7 hours after 8 a.m., that would be like a 15 o'clock, or if you prefer the 12-hour clock, 3 p.m. So we would have a maximum crowd size at 3 p.m. That is 7 hours after the park opened at 8 a.m. Now we might ask the question, well, how do we know that that critical value t equals 7 yields a maximum rather than a minimum? Well, there's a couple of ways that we could check that. One way would be by using the second derivative test. If we take our second derivative, we would have negative 400, which is less than 0, which means our function is concave downward. So at that critical value, we have a maximum rather than a minimum by the second derivative test. Now, another way that we could have approached this from the beginning is by noting that our function for crowd size is a quadratic. So its graph is a parabola opening downwards, and if we remember the formula for the vertex of a parabola, we could also get our answer that way without relying on the derivative here. And then in part C, so now that we've determined what time the crowd is a maximum, we ask what is the size of the maximum crowd. So to find that size, we take our function for crowd size p, and we evaluate at the time 7 when our crowd is a maximum. So using the function that we found in part A, we have 2800 times t, which is 7, minus 200 times 7 squared, which is 49. So this gives us a 19,600 minus 9,800, which is 9,800. So at 3 p.m., there's a crowd size of 9,800 people, which is the maximum crowd size. So let's look at some other examples. In this next problem, we're told that the marginal revenue, so that is the derivative of a revenue function, at a sales level of x thousand items of a product is given by r prime of x, which is the following polynomial function. So we're supposed to then find the revenue function. So if we have the derivative of revenue, or marginal revenue, to find the revenue function, r of x, well, we're going to take the antiderivative of the derivative. That is 50 minus 4x minus 3x squared, dx, since x is our variable. So finding the antiderivative of this function piece by piece, well, the antiderivative of 50 would be 50 times x, minus the antiderivative of 4x to the first power would be 4x squared over 2, or 2x squared, and then minus the antiderivative of 3x squared would be 3x cubed divided by 3, or just x cubed, and then plus some constant c on the end. Now again, for a problem, for an applied problem where our function has some physical interpretation like revenue, our constant c shouldn't just be any arbitrary number. There's some specific constant that should be used so that this problem makes sense with what we're talking about. So if we're talking about revenue, what other information can we use to solve for our constant? Well, we know that the revenue R at a sales level of 0, so if I'm not selling anything, then I have no revenue. So R of 0 should equal 0. But if we plug in 0 for x in the function that we just found, well, the only term that we're left with is the constant c. And this must be 0 since we have 0 revenue if we have a 0 sales level. So replacing our constant c by 0, we have the revenue function r of x is equal to 50x minus 2x squared minus x cubed. All right. So a very similar example, we're given the marginal cost at a production level of x units is the following functions. So the derivative of cost, which is marginal cost, is given here. And we're told that 6 units costs $32.50 to produce. So given this information, we want to find the cost function. So as with the previous example, if we have the derivative of a function, say the marginal cost, then the cost function will be the antiderivative of our derivative, which was 0.2x squared plus 0.4x plus 0.8 dx, since x is our variable here. So finding our antiderivative, well, we have a 0.2, and the antiderivative of x squared is x cubed divided by 3. Then plus, we have a 0.4x to the first, so the antiderivative of x to the first is x squared over 2. So dividing that 0.4 by 2, we have 0.2x squared. And then plus, on the end, I had a constant 0.8. Integrating with respect to x, we have 0.8x, and then plus some constant c. Now, again, this constant c that we're adding on the end shouldn't just be any arbitrary number. It needs to make sense in relation to the problem. So to solve for that constant, we're going to use the information that they gave us about the cost of producing 6 units. So here, the condition that we can use to solve for our constant c is that the cost at a production level of x equals 6 units is $32.50. So let's see what we get if we plug in 6 for x in the function we just found. We get a value of 26.4, and then plus, we're adding our constant on the end, c, and we're told that that cost has to equal $32.50. So subtracting 26.4 from both sides, we have the value of c is 6.1, which means that our cost function, c of x, is equal to 0.2 over 3 x cubed plus 0.2 x squared plus 0.8x plus c, where we just found c is equal to 6.1. So this would be our cost function. So let's look at one last example. So in this last example, we're told that recently there were approximately 200 million licensed drivers in the US, and we were told that 16-year-olds had 20 accidents per 100 drivers on average. So the rate at which the number of accidents per 100 drivers was changing as the driver's age increased is approximated by the function g of x, which is negative 10.2 divided by x, where x is the age of the driver in years. So here we're restricting ourselves to drivers of age at least 16 up through drivers of age 80. So given that information in part A, we're supposed to find a function that gives the number of accidents per 100 drivers at an age of x years. So in the problem statement, we were given the rate at which that number of accidents per 100 drivers is changing. So this function g of x, we're trying to find the antiderivative of to get our function. So we're going to define, let me call it capital G of x, as the antiderivative of little g of x, which was negative 10.2 over x dx. So that I can think of as pulling out my constant, negative 10.2, and then I have the integral of 1 over x dx, which, recall, is the natural log of the absolute value of x, plus some arbitrary constant c. So here g of x is equal to this function, and we need to solve for c here. So c, again, needs to be some constant that makes sense in relation to the interpretation of this problem. So looking back at the problem statement, we were told that 16-year-olds had 20 accidents per 100 drivers. So using that information, that means that the number of accidents per 100 drivers at an age of x equals 16 would be negative 10.2 times the natural log of 16 plus c, and we were told that that value has to be 20. So to solve for our constant c, we would have to add 10.2 times the natural log of 16 to both sides. So we have 20 plus 10.2 natural log of 16. And notice that in the problem statement, we were told to round the constant c to 2 decimal places. So by making use of a calculator, this constant c rounded to 2 decimal places is approximately 48.28. And so substituting that constant back into the function that we had for capital G of x, we have, it's running out of space here, capital G of x is equal to negative 10.2 times the natural log of absolute value x plus c, which we found to be 48.28. So this would be our answer for part A. This function gives the number of accidents per 100 drivers if the drivers are age x measured in years. So then in part B, we're asked approximately how many accidents per 100 drivers did drivers of age 18 have, of age 20, of age 50, or of age 70. So we're going to take the function that we just found and evaluate it at these ages. So for age 18, we plug in 18 for x. So we have negative 10.2 natural log of 18 plus 48.28. And using a calculator, if we evaluate this and round to the nearest integer value, this is about 19. So we were told 16-year-olds had, on average, 20 accidents per 100 drivers. So for age 18, it's only 1 accident less per 100 drivers. So then how about at age 20? Well, G of 20 is negative 10.2 times natural log of 20 plus 48.28. So rounding to the nearest integer value, we get 18. So 1 less accident for another 2 years of age. So then a little down the road, what about a driver of age 50, or 100 drivers of age 50? The average number of accidents would be negative 10.2 log 50 plus 48.28, which is approximately 8. And then for drivers of age 80, we have negative 10.2 natural log of 80 plus 48.28, which is approximately 5. Okay. So we're seeing as the age of the drivers increase, the number of accidents, or average number of accidents per 100 drivers, is decreasing. So then in part C, we ask, well, what reasons might account for these answers in part B? So why would we see a decrease in the number of accidents with an increase in the age of the driver? Well, there's several reasons that we could probably account for. Probably the most obvious would be more experience driving. Would lead to fewer accidents. Maybe as somebody gets older, they're driving less and perhaps more safely. So say not speeding, no texting while driving, so on. Or another reason might be, say, older individuals are driving maybe in more rural areas. They're not traveling to, say, downtown city areas or urban areas quite as much. So maybe in more rural areas might be one reason, or any other reasons that you might think of why an older driver might be less prone to have accidents.